Okay, so welcome to 474. It's May 17th. And I know you guys are working on the lab pretty hard. He's a gamer. Actually, no, I'm not. But yeah, I know good equipment when I see it. Okay, so anyway, so yeah, so keep up the good work and the good questions on lab 3. Somebody said that there was not an active submit button, but either the TAs jumped on that and fixed it, or I couldn't reproduce it in student view. It looks like that's working. Obviously, we want you to submit it, so keep on us if it doesn't work. And also, we are resolving for sure that we're going to get Lab 4 released before the due date of Lab 3. So there won't be delays, and we may even extend that due date to make sure you have time for it. It's going to be a great lab, and we will start introducing it just a little bit today. There's still a hand up. Jayanth, do you have? Okay. What is the workload for Lab 4 going to look like compared to Lab 3? It's really it's hard for me to know. The target we're shooting for on the labs is about the same every time, and I know it's not always the same. So, but it's an imperfect science to generate labs. So it's targeted to be the same, given that it also gives you more flexibility because there's going to be a mandatory component and a project component to the lab. So the project component will be under your control, and there's some criteria that project's going to have to meet. But not all projects will be as ambitious or involve the same complexity, and we'll talk about that more. So that's the best I can answer that. All right. So I guess any other questions, comments before we begin? Okay. As you know, and finally, one more thing. It's crunch time on Lab 3, of course, and the questions that come in to Piazza are fine, and I think we're more or less doing a good job keeping on top of those and answering them in time. And one thing I would ask is, if at all possible, make your question public rather than private. Maybe you're not even seeing that button or something, but if it's public, then we only have to answer it once and everybody else benefits. And hopefully nobody's making it private so that other groups waste time on the solution to a problem that we've solved. So I don't want to see that. I'm not accusing anybody of doing that intentionally, far from it. In fact, people are contributing answers to questions, and that's awesome. All right, with that, I'm going to move on and share screen. And let me know if you cannot see the screen, but everything looks like I'm sharing the screen. So we talked about serial data transmission last week, and it may have seemed, and it was in fact, that we were digging back way into ancient times and talking about like RS-232, which is from the 1960s type data standard, and much of RS-232 is not used anymore. But the key thing is that the basic concept of RS-232 is exactly the same in the most modern serial interfaces, which are I2C and SPI, some of which you guys have already used. They're used extremely widely with microcontrollers, including Arduinos. And basically, they make the modern cell phone possible, and we'll tell you why in a minute. So this is a board from the 90s, and it shows a trend that was just choking off technological progress. And that is, look at how many pins are on this chip. They're just, it's choking off the pins, and then the density of the board. And then look at the PC board, and so much space on this PCB is taken up just by running wires from all these pins. And this is almost comical today, but look how much space is taken up, and how much basically the progress of miniaturization was threatened to come to a grinding halt because of this issue of so many signals. This is a video card from way back, incredibly primitive by today's video standards. And one of the things holding it back was just how many pins you had to have. Okay, now we get up to a Nexus 5. This is more like the 2013 timeframe. And you look at this board and you don't see that. Of course, a lot of the traces are hidden, but you do see the traces, and there are fewer of them. Now, this is probably also a multi-layer board, and chips like this are typically, now this chip, you see the pins around the edge, okay? And you see little wires going around, not as many. And then this chip, you don't. And this chip is probably what's called a ball grid array, which means that there's actually a rectangular grid of little balls of solder on the bottom of the chip. And so they can use a 2D array instead of pins, instead of a 1D array of pins. But still, there's not this vast real estate devoted towards parallel lines like we saw before. And here's the SIM card interface for an idea of scale. And the camera down here. So there's like, I think that's the camera, pretty sure. So this is a lot of miniaturization. And again, and we don't waste a lot of space on that. Here's the motherboard for Google 5, Pixel 5. So this is today's state of the art. And this is one of those teardown. Actually, this is a good thing to look at. If you've never seen these, here's a Pixel 5. And the teardown is a slideshow. So they take the screen off, and then they start prying a few things off with one of those tool kits. Now there's many screws to remove. And a battery is, you can see the battery takes up a lot of space. We all want a big battery in our phones for obvious reasons. And now popping a retaining clip off, that is the phone. Think about it. That is your cell phone. Not only your cell phone, but a state-of-the-art, top-tier cell phone. And so somehow, and it's not just one chip. So these don't look like chips because they come in metal cans to shield them because of the radio frequency interference problem inherent in cell phones, and this also inherent in this tight packaging. So the chips are inside here though. And again, this cell phone is hundreds of times, thousands of times more complex than that graphics card from the 90s, and yet you don't see the wiring. What else can we get here? Flipping it. And this is the back of the cell phone where you get camera ports and a few other goodies for the cell phone. Okay, so that was a little tour. And so how do we achieve that? We achieve that by cutting the number of wires. And this problem was starting to become apparent in the 80s. And Philips, the Dutch, oops, that's not what I wanted to do. Philips, the Dutch electronics company, which has a new name at NXP, developed the first one, I2C, inter-integrated circuit bus. And we talked about buses before as parallel arrays of lines, but this is a serial bus. And they figured out that because you're just going from one chip to another on the same card, some of that noise immunity isn't needed as much. You've got very short runs, you've got better signal conditioning, so you can run this quite fast. And so it's feasible to eliminate so many pins by sending serial data. So I2C is only 2 wires, and therefore it's only 2 pins per chip. And they're called serial clock and serial data. Couldn't be simpler. So before we get further into both of these, we got to talk about terminology. I don't know why I'm double clicking stuff. So when they talk about sending data back and forth, you will see over and over the terms master and slave. And those terms are very offensive to a lot of people, especially Black, Indigenous, and people of color. And so we're not going to use those. We're just going to say leader and follower instead, okay? Because it's true that one of these chips will coordinate and the other one will respond. And if you're taking 398, if you took 398 from me, you know my journey on this. I've used those terms for years. You could look on Google Scholar, you'll find hundreds, literally hundreds or dozens of publications by me using those terms. And my thinking has really evolved because I just think that bottom line is, if people find this term triggering, offensive, and suggestive of very painful cultural memories and traditions, it's really honest to honor that and push back at the standard terminology. So that's what we're doing. Okay, so here's an I2C bus. It's got these 2 wires, serial clock, serial data. It's got a microcontroller, which is the leader, and it's got 3 devices, which are followers. And so, okay, how does that work? Well, the microcontroller, or actually any device, can talk on the data line. And that's why there's an external resistor here. So these devices can sync current, but they can't source it. So they can pull the line low, but they can't raise it high. And this is a way you can have different devices sharing the bus, because when they aren't pulling the line low, when they're kind of like outputting a logic 1, then another line could bring it low. Another device could bring it low by drawing current through this resistor. For bipolar, you call this an open collector or an open drain bus for MOSFETs. And then the clock is generated by the microcontroller. It's a one-way signal. But it's asynchronous. Well, it's not asynchronous because it has a clock, but it can be idle. So the idle state is when both lines are high. And then this event right here, where the data line goes down and the clock line stays high, is called a start condition. It's really an event. It's the transition from high to low of the data line. And then everybody starts to pay attention and data comes through. And then there's a stop condition, which resets the bus which is sort of opposite. The data line goes back to logic 1. But how do the chips know what the data means? So this is a packet, or set of packets. This is the setup here. And so the leader creates the start condition, which we just saw there, by driving the 2 lines. And then it sets 7 address bits. And chips that support I2C just come from the factory with a particular address burned into them. So you want this particular DAC, or you look up what its address is and you write your code that way. And then it also sends this 8th bit, which is read or write, meaning does the leader want to get data from the device or write data to the device? And then the follower, if it recognizes its address in these 7 bits, sends an ACK or NACK, which is a 1 if it's an ACK. So then that means that the follower has recognized itself and it's ready to either send data if it was a read request, or read data if it was a write request, if that makes sense, because these R and W are with respect to the leader. So then we start transferring data, and depending on which direction this bit is, the data line is controlled by the follower or the leader. And then whichever is the other side, and this, okay, so this line I drew here is, oops, God, I'm not used to doing present mode, I guess. Probably should be a dashed line and also a dashed line from the leader over here, because if it's read mode, the leader would be sending these ACKs or NACKs. And I don't think the ACKs or NACKs are based on a parity, because there's only 8 data bits. So I think this is just simply, I'm not sure how it detects an error. If it doesn't ACK, though, that's an error. And this can be repeated. It's not really shown graphically, but this data byte can be repeated as many times as necessary, which would be specific to the individual chip. Like the individual device may have 4 registers of 8 bits each, or it may just have 1 or whatever. And then the stop condition is asserted by the leader. And then it's done. So those of you who are paying attention may recognize a problem that there's only 128 possible addresses in the whole universe of I²C, but there's a lot more chips out there than 128. And so, in fact, there's an interesting list at Adafruit of I²C addresses. And, for each address, there's, here's one with 4 different chips. So if the address is 2B hex, then you've got this capacitive touch center, you've got a sensor, you've got a digital logarithmic potentiometer, you've got a digital 10K potentiometer, you've got a temperature sensor. And these are just ones that Adafruit is interested in. There's probably others. Let's see what the record is. See, 40 is a huge number. So that's kind of a problem. I mean, you may get lucky that your devices that you care about have different addresses, but you may not. So what to do? So there's the main solution is to get other bits involved. And most chips have some kind of enable signal as an input. And so here's an example of 2 chips, and they have the same address, OX3D, and they're on the same I²C bus, and you use additional pins to switch them on and off so they don't collide with each other. Okay. Okay, the other big one that's out there is SPI, Serial Peripheral Interface. And it addresses the same thing. And Motorola was a much bigger semiconductor company back in the 80s than it is now, or at least bigger market share and mind share. And, companies are proprietary. They don't want one company to set a standard. So let's develop another one. Oh, by the way, this is official documentation. I guess I2C is kind of a copyrighted term. It's really simple to implement. You can't, they don't really enforce patents on it or anything, but it is owned by this company, and we'll see where that shows up. But you get documentation, documentation from NXP about the bus. And there are other modes that are less often used. So for example, this 7-bit address is limiting, so they have another mode where it can be a 10-bit address, but that's very rarely used. So this is the more common way it's used. There's a couple other features that, from everything I can tell, they're just less widely used. So SPI has 4 wires, not 2. The advantage is it doesn't have addresses at all, so you can't run out or duplicate addresses. So that's the trade-off. And the 4 lines are MOSI, which is microcontroller serial input, and MISO, microcontroller serial output. And yes, I've adjusted the terminology. And then a serial clock and a select signal. And because I guess it's a little more proprietary, because the best reference I could find was Wikipedia rather than some Motorola thing. So how does that work? So basically it's shift registers, and data is clocked through a shift register from the leader to the follower in every case, but it's kind of in this circle. So in the process of writing to the follower, the leader also gets all the data from the follower. Kind of elegant. And so how do you do multiple devices? So one of them is chip select, just like with I2C. And so the secret sauce is these chip select lines, which involve additional pins to the select lines on all these devices. So 3 devices, 1 microcontroller, and select individual ones. And then the serial in and out lines are shared. So this is good because you get individual access to the chips, but the negative, and in fact, you can read a chip faster, and you'll see the alternative is slower. You'll see why in a minute. And then the negative is you've got to use extra pins. But there's another way to do it, which is, I call it the big loop method. And so you just have 1 select, and you wire them in series in a daisy chain like that. So the bits come out of the microcontroller and they work their way all the way through. So like your software has to understand this topology pretty well, right? So like if there's 8 bits, if device 0 has 1 register of 8 bits and device 1 has 16 bits and device 2 has 8 bits, you've got to shift out 32 bits in the right arrangement so that when you've clocked it 32 times, you get the correct bits in device 0 and the correct bits in device 1 and the correct bits in device 2. And you know that's I think you can figure out how to do that. It's not super hard, but it's something you got to pay attention to. And then also, of course, you read them in through here, so you just got to remember exactly what sequences are wired up so that you can unpack them later. So the good thing is you don't have those extra pins consumed, but it's slower because you've got to do them all at once, at least to read. Even like you can imagine an application where you have to read device 0 a lot, like really fast all the time. But device 1 is just once in a while you read it, and device 2 is just a special case. But with this wiring, you're going to have to read all of them all the time, because in order to read device 0, you have to read them all. And so that could be an architecture decision. This is where embedded computing is really embedded, right? Because it's like this decision in terms of PCB layout, it affects printed circuit layout because it's fewer pins, and maybe it's even easier to route this than separate lines to all of these or whatever. But the software and even the performance might be quite impacted, especially if there's a sort of asymmetry in how fast you need to access all of these. So it's like from the software to the printed circuit board layer, all those decisions interact. That's why this is embedded computing. On our chip, there's special hardware to support spot SPI. So here's the 4 bits that are pins, dedicated pins on our chip. And this is just, figure 21-1 from that data sheet, 350-page data sheet. And it's just like, with the timers, there's control registers, and you would set bits in here to control it. And you would you put your data in here, and you either read it or write it according to what you're doing. And depending on who's hooked up to these lines and how many registers are hooked up out there, you will read or write a different amount of bytes. And of course, this can be set for an interrupt so that it will clock the bytes out at a certain rate, but it won't bother your code until it needs another byte to be uploaded. So anyway, it's sort of an automated process in the Arduino, in the ATmega, and this is hardware that may or may not be present in different Arduino chips. But Mega is called Mega because it has a lot of stuff. Okay, and there's also I2C, but I think because of this copyright or proprietariness in the name, they call it the TWI, which is two-wire interface. Okay, fine, but it's compatible. And interestingly, this is like a diagram that doesn't sort of read the same as all the other diagrams in the document. If you notice, is a professional communication issue. We're used to these from the timers and the other features of the ATmega, where you see each bit has its name labeled, and it goes to different places, and you see all the connections and sort of what goes to what. Of course, this diagram is certainly not sufficient to tell you everything you know, but it has a lot of sort of detail. Whereas this one is more of a block diagram. It's okay though. One thing you can learn is that these heavy outlines are the registers that you're allowed to twiddle or access when you're programming. And otherwise, it's more sort of functionally organized. And this is the bus. The data comes in here or goes out here. And you can set the bit rate right here. There's a pre-scaler. That should be a familiar concept. So using detail. Everybody. Yeah, I don't know why. It also, I have to say, it seems like this thing is more common in class than in, say, a faculty meeting or something. it may have to do with this screen share. I don't know, but it doesn't happen in my other meetings. It's just you guys, I think. But at least I've got you trained to let me know now, so thank you. All right, so anyway, you can also get hardware support for I2C/TWI. And then it's kind of, we can look at some software examples. Again, regrettably, we're not going to use these. We're not going to have detailed lab assignments on SPI and I2C. I encourage you to use them for Lab 4 if they make sense. And some of you, many of you used it for Lab 2 with the 8x8 matrix. But I'll just sort of walk you through some of these, and I apologize for the terminology, which is, again, I think you're going to see, mark my words, it's going to be slow because it's so baked in, but mark my words, you're going to see this terminology changing from these companies. So here's an SPI driver on GitHub, and well, that's just how to use it. And basically, they're, setting up the, they're initializing the SPI device, which is that device I showed you, and then this is DDRs. So as you know, this is data direction registers, which is just making those pins into outputs so they actually drive the bus, and an input for the microcontroller input data, and then enabling those other pins, and sending a byte is polling and waiting until an interrupt flag is set. But there's basically, yeah, so here's like sending a string over SPI. So while you go through the string until you hit that 0 at the end, and I think I can make this a little bigger. Maybe that'll be easier to see. I don't know. And then you send each byte and increment your string pointer. But I was interested in the lower level. Oh yeah, see, the lower level is very simple because of all that hardware automation. So you just copy your byte into the data register. Done. It's sent. And this is polling, and this is actually software that would not work well with our current schedulers, because this is just an infinite loop until the status register says it's done sending that byte. And so this means 100% of the time will be taken up by the SPI data transmission, which is wasteful. But this is a very simple, the nice thing is this is good, easy to understand code, and it's in some applications you don't care. Also in some operating systems and some schedulers. So we're going to see that this would actually be okay for FreeRTOS that we're going to use in Lab 4, because FreeRTOS is preemptive. So it can just bust in here and run some other task for a while. Okay, so that's this driver. And then two-wire interface is part of the standard Arduino AVR library, which actually comes from, I believe it comes from the manufacturer. And this one's messier, and I'm really not sure if that's inherent or just sort of a different way of coding. And I haven't dug in yet to see if that's right. It's using C++, hence the CPP file extension, and that sometimes makes software seem more complicated, but maybe more scalable. And that's what this semicolon thing is. It says that there's a class. This is a two-wire class, and it now has methods that belong to it. And so anyway, it's a set of functions to initialize it and to send data and setting timeouts and so forth. And I won't go through completely through this, but it's also there for you to look at. Let's see if there's anything specifically good. Okay. Yeah, so anyway, it seems like it's a lot longer to do essentially the exact same thing with a lot of hardware support than that other driver. And I'm not sure exactly, again, as I said, I'm not sure if that's strictly necessary or not, but that's what's in the Arduino's library. Okay, you will see on various web various things out there, bit banging as an alternative. What does that mean? What it means is you just you don't use any hardware, and you may have a different chip which doesn't have any hardware automation for I squared C or SPI. So you may have to do this. And so you just pick digital IO pins and assign them to those functions. And then you write code that just raises and lowers the bits to generate the to operate that bus. And so the advantage is that's completely portable because it doesn't assume any particular hardware. But the negative is it's much slower, and it blocks all the other code. It can't be interrupt driven or things like that. And here's another one. Sorry, this one in GitHub has in fact, Git has this name master for the default branch, and a lot of people are changing their branch structure to be main. Main is a perfectly good name. Actually, just to go back onto this subject, not only is master slave offensive to a lot of people, but in many cases, what you find when you sort of start rethinking it and looking for a more acceptable and inclusive naming system, you realize, hey, wait a minute, that isn't even a good analogy anyway. It doesn't actually really tell you anything, and so it's actually doubly harmful. And in a way, that's true of the master branch. It's the main branch or the default branch or anything. Anyhow, this one is just got some setup, and then so here it's a low-level thing where this code is flipping bits up and down. The clock high, a little bit of delay, the clock low, and then a little bit of delay. So it's all right here, and that's actually kind of easy to understand. It's just that it's slow and it blocks the whole. This is really it, right? And this is one way. This is sending it. Well, no, it was for SPI. It's always two-way because it's that loop. So this is kind of nice. It's simple to understand, but it's inefficient. Okay. So yeah, it uses the bad wording twice. Okay, that is it for I squared C and SPI. Are there any questions about those two technologies? Okay, so with that, we're gonna take a break until 3. Let's say let's go to 3:25 and make it 10 minutes. Then we'll talk about the operating system we're going to install for the Lab 4 projects. And now that you understand what schedulers are and how they work, we're going to use a even better one. So I'll see you guys back in about 10 minutes. All right, let's resume. Welcome back. I'm going to go. So what we're talking about now is FreeRTOS, and that is a small operating system that you guys are going to be able to use. There's a question on chat from, actually it's quite a while ago, and I did answer it, but just in case, yes, we pledge that we will release Lab 4 on Wednesday evening at the latest. So there will be, yeah, so that's when we're releasing it. Okay. All right, so this is an open source mini operating system for little boards like the Arduino, and it's been ported to many different chips, all the different Arduinos and other boards like STM32 and PIC microcontroller and the, excuse me, many others that are out there. From what you see online, it's got a lot of support from Amazon.com, but it's definitely fully open source with a very flexible licensing, so Amazon doesn't control you if you use it. And I believe that it predates Amazon or at least predates Amazon's involvement by quite a while. So from what I can tell, and who knows, maybe it's controversial, but from what I can tell, it's just a good thing where Amazon's putting resources into supporting it, namely programmers who improve it. Okay, so it's open source, it's small, so it's not as powerful as an embedded Linux or a stripped down version of Linux. It's not intended for that market, but it's for very small chips and or chips comparable to this. The biggest difference you find when you move up to the more Linux-based or even Windows and operating systems or Android, but Android has Linux inside it, and so does the Mac. At any rate, the biggest difference is whether the chip supports protected memory management or not. And in that case, each task is in a protected block of memory, and it will be stopped if it tries to write or read data outside its own block of memory. So that means one task cannot break all the other tasks, which is sort of a huge step up. We still have schedulers, like all of our schedulers operated on kind of an honor system. So if any task wanted to, or it was controlled by a malicious hacker, it could easily, without even the slightest effort, it could easily just kill the system, for example, going into an infinite loop. But many microcontrollers don't have the amount of silicon to dedicate to that function. And so they operate like these more simple chips. And for that, you can use a much simpler operating system and save space. So like the binary for the FreeRTOS is just like 5K bytes or something. It's just amazingly small for the kind of projects that we use. So the main things that it has is it has a scheduler, which is preemptive and priority based. And we'll go into that in a little bit. And it has features called queues for inter-process or inter-task communication. So if we need one task if we need one task to communicate with another task or share data, we have to be a little careful. We have to say have a global variable between the two tasks, and we have to make sure we understand when one task is done and the other task is ready. And once, for just a flag, like when you see this bit do something, it's not that hard. But if you have a buffer of data that you need to process from, say, a camera or a sensor that acquires blocks of data, then you have to be much more careful that the destination task or doesn't, for example, start processing a half a chunk of data instead of a full chunk of data. So queues can manage that kind of stuff, and you can, your task can call a FreeRTOS call and say, let me wait until a queued packet is ready and then give it to me. And we'll talk about that a little. I'm gonna go ahead and talk about the big picture before we dive into these links. So preemptive is something we haven't done in our schedulers yet, and it makes a big difference. And it says the scheduler can use interrupts from its timer to break into tasks that are actually running. So all of our schedulers have relied on each task doing a tiny thing and then returning. And by doing that over and over, they get real work done. But it's a sort of artificial constraint on the programmer, right? So you want a programmer to just function on one task, focus on one task, and not worry about all the other tasks and not worry about scheduling. That's the ideal, right? So when you have preemption, it really helps because you can write your task like this. While one, so forever, just do stuff. And then maybe if you want to do stuff periodically, you just call a delay and keep doing it. Okay, so maybe flash an LED. So do stuff would be toggle the LED, and VTask delay would be 5 ticks or whatever. But you don't even need to have the delay, because that's where the preemption comes in. You can just work, and the interrupts will break into your task and maybe start another task for a while, but come back to your task so you can finish your work. So that's quite a nice thing, and it's it's quite a nice thing. And also priority base. So the tasks have a priority level. And when we did that scheduler diagramming exercise a couple of weeks ago, we saw times where, a couple of tasks would be ready, and it was a little arbitrary which one do we run. Now, in round robin, you just keep going around, and that's sort of fair, but fairness isn't always the goal. And sometimes tasks can just step to the rear of the line because their priority just isn't that high. So you can implement that by in this scheduler. There's a task descriptor block, just like we did TCB. It's not called that, but you initialize that when you start every task, as I'll show you. And if you give it a 0 is the lowest priority, and a 4 is the highest. Well, it's configurable. You can adjust RTOS to have up to 32 priorities levels. That's kind of a lot. But it starts out at a default of 4. So you get 0 to 3. are your priorities. And once you've installed FreeRTOS, you can set these things in the configurations and the variant .h files, which are in your libraries directory where you installed any other libraries that you might use in an Arduino application. So scheduler ticks. So we've been running 1 millisecond ticks, very fast. On the other hand, you've got to admit, I've got to admit, we've got to admit that our tasks have been very simple. Sure, sometimes they're challenging to program, but they don't exactly do machine learning or solve the traveling salesman problem or anything like that. In FreeRTOS, the fastest option is 15 milliseconds. And you can find out what your scheduler rate is by the port tick rate Hertz defined symbol. And the versions that we will use are set to 15. And it's interesting to figure out. I personally have been playing around and trying to speed that up, but it turns out you can't. And I figured out why. So for faster things, we should do ISRs. We can set up a timer and do ISRs, at least in theory. TBH, I haven't gotten that working yet on this board. But the good news for you is I wasn't planning on assigning those anyway. So if I get it working, I'm going to proudly show it to you, but I don't think this is going to impact you. Another tip on FreeRTOS, a lot of times you'll see people talking about ports in all kinds of documents and code. And this is a different notion of port than we've been using. So as you know, the chip has a whole bunch of ports, A, B, C, D, E, F, and G, and each port is 8 bits, which map to pins, and that's great. And it's still true. However, in FreeRTOS, this operating system supports many different chips, probably dozens or hundreds. And what they've done and what operating systems have done for a long time is they factor out all the code that's specific to a particular machine. And when you get into servicing interrupts and dealing with timers and things like that, every chip is different. And so to the maximum extent, all the FreeRTOS code is the same for every chip. Obviously, they really try to hide those differences from you, the programmer. They want to make it so that you can develop in FreeRTOS, and then if your boss or your company or you decide to switch to another chip, you don't have to write everything from scratch. That's their goal. And I think it's overall successful. So anyway, a port means porting FreeRTOS to a different machine. So when they say port specific stuff, they don't mean port B. They mean it's specific to the Arduino ATmega 2560 or the PIC something or other, or different chips. So just watch that. That'll save you a few minutes at least when you're reading the document for the first time. So how does the FreeRTOS scheduler do ticks? We did it with a 16-bit timer, but if FreeRTOS used one of those timers, then the user could not use it, and it would be hard to predict which one it was using, and it would be hard to standardize. Anyway, in the Arduinos, they use this other timer, which we didn't talk about, called the Watchdog timer. And so I'm going to introduce that, and it's a very important concept actually for embedded systems. And so this is a good time to go into it. So this is, I forget which chapter, it's near the beginning, like page 65 in our data sheet. So the benefit of using this for the tick system of the scheduler is it doesn't use the main timers, and therefore people just assume, if people assume they're free, they are free. That's good. They're available. The minus is you can't have watchdog timer functionality. So what is watchdog timer functionality? We'll get to that. So as you build a port and you or adjust your preferences in this file, I think it's in config.h, or it might be in variant.h. You can set what you want the scheduler period tick to be. And unfortunately, from my point of view, the fastest is 15 milliseconds, but you could get it as slow as 2 seconds if you wanted. And that's because this timer has a prescaler, just like we've used in the other timers, and it has similar divide ratios, but it's only a 128 kilohertz oscillator. Generally speaking, watchdog timers want to run at slower rates, and we'll explain why. So what's the point? So watchdog timers are very widely used in real-time, safety critical, mission critical, medical, all that kind of embedded system. And they go way, way back. And the purpose is to protect a system from a software crash, because unfortunately those happen even if you think your software is perfect. And the way it works is that and here's the thing, you can buy them. This is an external example that you can just buy. It's a piece of hardware. In some ways, an external watchdog timer is a very good idea because it's completely separate from your software development team. So it can't have any common assumptions, and so it'll just work, hopefully. So the way it works is that this timer is connected to the reset button of your system. And it has an input, a digital logic input to it as well. And every so often, the watchdog timer has to be reset by a pulse from your software, not a level though. So it has to be a pulse, it has to be a level change. And if the pulse is received, it resets. But if the pulse is not received after a certain time, the system gets a hard reset. And that way, if this is a temperature controller on a refrigerated trailer truck that's crossing the country with a bunch of steaks that are worth $1 million, headed for New York City, if that refrigeration unit dies, you lose a lot of meat and a lot of money. And if it dies because of a software glitch in a microcontroller that's controlling the refrigeration unit, that's a shame, because it, what if it's just a software glitch and you could reset it? So you have this watchdog timer. You have to write your code so that it remembers every 1 second or every 5 seconds or something sort of modest, every 1/10 of a second, whatever you think is right. It sends that pulse to the watchdog timer. And therefore, the watchdog timer knows the software is alive, and it does not reset the system. But if the software gets hung in some task that goes into an infinite loop, or the stack overflows or something and it just can't run, then the watchdog timer will just reset it. And maybe that was a rare, maybe it runs most of the time just fine, but there's a very rare set of circumstances where that bug is exposed. And in fact, this is another thing that happens in those Mars landers, like the one that JPL landed, and of course now China landed one. They probably have watchdog timers too, but I've read specifically about watchdog timer resets in JPL rovers. Okay, so even though they test it so much on land in Pasadena before they launch it, they think of every possible thing and they try it and they simulate the mission in as much detail as possible. It's just a little bit different when you're actually flying to Mars and actually landing on Mars. And so they know that there's still a possibility the software could lock up, and so they have Watchdog Timer. And then when it wakes up from the reset, it sends data back to Earth and says, well, this happened and I don't know why, but here's everything I know. And it sends back the state of the whole system. And then JPL decides what to do next. So anyway, it's a very important concept for embedded systems where they're critical. And external hardware is a good way to do it. I'm sure that's what they do in the JPL one. And also another feature that's designed for security and reliability, because what could happen, it would be rare, but it could happen, is that some task in your system goes a little crazy and starts writing random bits at random. And what if just by bad luck, it randomly reconfigured the Watchdog Timer to not function anymore? Then the system would easily hang up and the Watchdog Timer would not reset it. Now, this would not be a factor with an external hardware-based Watchdog Timer, but it would be a factor with this internal one in the chip. So what about that? So there's actually a special fuse in the, and fuses are bits that you can program one time and they're permanent. And if you want to change it, you're out of luck. You have to literally throw the chip away. So you can do things like burn in a serial number or set a few permanent settings in a chip. And I didn't ever look up what the other fuses are on our chip. That would be an interesting little thing to study. But there is a special fuse inside our chip called WTON, and you can set that and permanently set up the Watchdog Timer so it can't ever be changed ever again. You got to know what you're doing and debug your software. Also, in terms of the onboard inside the chip Watchdog Timer, this one in particular, it has two different outputs which you can enable. One is interrupt, where it doesn't kill the system and reset it, it causes an interrupt. This is how RTOS is using it as a scheduler tick. And the other mode is it can cause the hard reset. So obviously RTOS is disabling that mode and just using this kind of like one of our other timers to generate a periodic interrupt. Okay, that's why I said it's a minus here, that this choice by FreeRTOS means we can't use this as a Watchdog Timer anymore in a meaningful way. Now, there's also a possibility where you can turn both of these on. This is a clever thing too. And it can cause the interrupt. And then later, when the interrupt is done, it can cause the system reset. And you might have software which would really like to save its state, perhaps with an error log, and say, where was I when this bad thing happened? And it could save that into the EEPROM and then do the hard reset. So that's another option this very interesting flexible timer has. Okay, I'm going to go back up. Yeah, so I said I'm going to show you an app that I'm working on with FreeRTOS as an example. And I don't know if I'm sharing the screen right. Just to be sure, I'm going to start it and stop it. Here we go. Okay. You guys should see an Arduino IDE interface. If you don't, you know what to do. And this is called 7seg FreeRTOS. And so this is an RTOS option demo, and you have to include FreeRTOS. This is one I wrote, and what we're going to set you guys up with a working demo app so that you can do the installation and easily verify that you've got it working. You won't have to start from a blank screen. But anyway, you include FreeRTOS.h, which is all the definitions. You install it in your Arduino library. And there are, one of the problems and opportunities is that there are very many versions of different ports of FreeRTOS to the Arduino. And they have small differences and they have different names. And so this one is Arduino_FreeRTOS.h. And we haven't finalized that this is the one we're going to assign to you. But you're going to get that word shortly. And so I have a bunch of things for driving. You must have figured out similar 7-segment stuff for lab 3. And now we're doing some setup. And this is where we get to FreeRTOS code specific setup. So we're going to create tasks. And this is the arguments to the X. For some reason, the FreeRTOS calls begin with X and V, lowercase x and lowercase v, and I confess I don't know why. But at any rate, task create is just setting up a TCB for this task. And first thing is, this is a little funny syntax, but this is your function pointer for the task's function. And then you give it a name, and then you give it a stack size. And as you recall, the stack is where everything is stored when it does function calls, and not for interrupts. That it will be a separate stack, I believe. It doesn't count against your stack size. But this is one of the sort of professional level embedded systems decisions, is how much space do you allow for the stack? If you allow too much, you're wasting memory. If you allow too little, there's always that danger that the stack will overflow the available memory, because it's hard to know in advance how many levels deep you're going to be making function calls, if not impossible. In fact, stack overflows have also happened on Mars. And so anyway, that's just an interesting little fact. I forget what this one is, but in all the examples I've seen, it's null so far. So that's what we're going to do. And then you set your priority level. So so in this case, blink is the highest priority. You can guess what blink does, and we're going to see the code. And there's a configuration of the max priorities, and so 0 to 3 is your range basically by default. So this is the highest priority, and then this last one is a pointer where it will replace that. It will point that pointer to the task. So it's called I think it's called a task tag. So if you need to know the name of a task for some reason, and there are reasons, like you want to control some other task within your task, then you would put pointers in here, and we'll try to, if we need that, we'll put an example in. But when it's null, then this is ignored. But you notice that as there's no return value from task create, so we don't have a tag for it, a way to talk about it, or a label for it. But to first order, for many systems, we don't need it. Here's another one. Just scan the 7-segment display. I've turned it off right now. This is easier to do than with comments because it's one character instead of stars and slashes and stuff. So this is we will be getting to this, but right now it's turned off. And then there's another task which just counts, and that will drive the 7-segment display. And then we start the scheduler, and we're done with setup. And all right, I'm back. Thank you. But I'm going to check chat just in case. I think it's there. Yeah. What happened to chat? There. Yeah. All right. Yeah. So anyway, with many of the examples I've found say at this point, scheduler starts automatically, and that comment is there. And I couldn't get anything to start until I actually manually started the scheduler, and then everything worked. And I think this is, again, it's going to work slightly different on every port. When it ports the operating system to each different chip, there are slight differences. So I think that's what bit us there. But the good news for you is I've solved that. So this is wrong. You actually have to manually start the scheduler. Okay. And then in RTOS, the loop is empty. It's just nothing. So just leave it empty. And then we have our tasks. Okay, so for example, task counter, it has a count variable, which is static. That's important, so it remembers it each time. And then forever, while one, we're going to just increase the count. And if the count's greater than 99.99, we'll reset it back to 0 since I only have a 4-digit display. And then I have a function which converts the number, which is an int, into 4 digits. So because that's how I chose to implement this. Later on, we'll convert the digits to segments. And then we're going to delay for 50 operating system ticks. And since the tick is 15 milliseconds, 15 times 50 is 750. So it's going to be 3/4 of a second. And actually, I don't remember the symbol, but we'll get that to you. Sometimes in examples, you'll see the following instead. Okay, and so this way, this will take, we wanted 750 milliseconds. And if we divide it by the tick time delay, and the reason I'm not actually typing it into the code is I can't remember right now the exact symbol for this value, but this is 15 milliseconds. And so then it divides it, and now it knows how many ticks is the right value. Because again, this is in units of 15 millisecond ticks. Okay, so sometimes you'll see this division, and that's what it means. It means the programmer wanted to specify milliseconds, but the tick rate is not milliseconds. Okay. And then display scan is not running. And actually, I don't even need most of that stuff anymore. But the way we're going to do it is, while one, we're going to go through the digit positions, 0 through 3, and we're going to light up the digit that's selected, and we're going to get the digit value, this is actually, this is using a global, so it's a little unclear, but this is getting the digit that we want to use, like 7. So this is identify 0 through 9. And then I have this big set of 1s and 0s, which tells which segments are lit up for which digit value, like 7 is this and this, okay? And then light up the segments. And then we're going to delay for 15 milliseconds. And then we're going to clear the segments and delay for another 15 milliseconds. So it's going to be on and off 50%. And then we're going to go to the next digit and repeat. And so we can call delays, but we don't have to return ever. But that task is not, and then there's various functions, like this is converting the digits, the 4-digit number into individual digits. All right. All right, and some of this is lab 3 stuff, so I'm not gonna share that code with you. Okay, so let's see what it does. It compiles, and I'm gonna download it. And oh, and I didn't show you Blink. Find it. Maybe it would have been easier to scroll. Okay, task Blink. And basically, it's very simple. So the first time we execute it, it sets the pin mode, which is, I actually also did it in setup, so this is probably not important. This is just another way to write an infinite loop. I think while one is better than this actually. And then we're just going ahead and using Arduino functions because basically I got this demo from these two folks. And so we set the built-in LED on. Oh, here it is, port tick period. So here's an example. So we wait for 200 milliseconds. By the way, this is approximate because it's an integer divide by 15 milliseconds. So that's not going to work out exact. So that's a thing to keep in mind. And the comment's off because I just wanted to speed it up. I thought this was too slow. Originally, that was 1,000, of course. And then we turn it off and we have another 200. So this is a total of 400 milliseconds approximately with an on and off. And right now, and counting is a simple task too. I already showed that. We're just counting, resetting, and delaying for 50 cycles, whatever that worked out to, 750. Okay, so again, it builds and I'm going to download it, but I'm going to first switch. I think I'm going to stop share and switch to you guys should go on speaker view so you can see my little circuit board better. I think you're not going to be able to see the display update very well, but you'll see that we are, oh, I can turn this off. Okay, so I'm going to download, but it's not downloading. Why not? Uploading, actually. There, it's uploading. And now you see the little light flashing on and off, and that's 200 on, 200 off. Okay, and then now we're going to enable the display task. And what do you guys predict how this is going to look? Just spend 1 second thinking, how is this going to look? So to enable the task, I'm going to go from 0 to 1 here. And now we're going to also start the segment scanner. It still compiles. We're going to upload. It's uploading. And now, oh, it actually comes across, at least what I can see, if I pin the video, pin video. Yeah, so you can see what's happening. Actually, this is reversed on my screen. Maybe it's not reversed on your screen, but you can see it's counting. And in reality, the segments are not reversed. And you see it's very flickery. Okay? And so that shows you some tasks. Unfortunately, I found with Lab 3 that you can't fuse them and get rid of the flicker until you get down to about 5 milliseconds per digit, which should be feasible for Lab 3 with our 1 millisecond scheduler. So, okay, I am going to wind up. I think I had one more slide actually, or two to go over, or one more thing from a slide. Oh yeah, right. So interrupts. I want to implement an interrupt. I want to interrupt and I want to implement an interrupt service routine to scan the 7-segment display so I can do it every 5 milliseconds and make it rock solid and not flickery. And so I'm working on that. But to be honest, it's not working yet. It freezes the system. And what are the what are the complexities? And I just wanted to show you. So this is what remember we used a macro before, ISR, and I told you that that appended and prepended magic codes to before and after your ISR to protect everything else. Obviously, that has to be done exactly right, and also that's machine architecture dependent. And so this is what the code looks like for. I'm going to. You're not seeing that yet. Okay, you should see now some pound of fine in the upper left, ISR down in the weeds. And so this is the code called port save context. Port again meaning specific to our chip. And I think the problem I have is not having this set right so far. Anyway, what you're seeing here is actually assembler, machine language, where each line is exactly one machine instruction. And because stack operations are so common and they're done every interrupt, every subroutine call over and over and over, they are implemented completely in hardware and they're fast. And so push R2 means the second register in the processor register 2, push it on the stack, copy its value to the stack pointer, and then increment the stack pointer. And so this is pushing all the CPU registers, and there's 28 of them, onto the stack. And I don't remember what LDS is. We're not learning assembler, perhaps a good thing. And there's these other instructions, and I haven't really figured out what they do. And the good thing is I don't need to know what they do. But I just wanted to show you that all this happens just at the beginning of an ISR to make sure that your ISR can use the registers without erasing what was in them. Because after your ISR is over, there's a similar thing called port restore context, or and the similar code pops them off the stack in reverse order, because whatever was put on the stack last is the top of the stack. So that's a lot actually with 28 registers. The good news is each of those lines executes in a very small number of microseconds. And it depends a little bit on what instruction it is. But the good news is this takes very little time, but it is a lot of work and has to be done exactly right. Otherwise, the ISR will fail. Okay, that's all for today. Except for questions, I'll throw it open.
Hey, Professor, is it possible you could go through how exactly task 5, like overall, is supposed to run? Because I'm still a little confused.
Have you been following the
Yes, I have been reading the
Piazza? Okay, because we've tried to clarify it.
I'm
Yeah,
still a little confused.
yeah, that's fine. I'll do what I can. All right, and I'm going to share that if I can find Zoom again. Okay, you should see tasks for the Lab 3 document. Everybody see that? And there are a bunch of people already on the document, which is great. So task 5 is, the idea is that task doesn't do anything. It just controls other tasks. And so it should start task 1 and just leave it alone. Task 1 should do its thing, which is flashing an LED. And then it should start task 2 also. But after it runs twice, it should stop. Okay, so let's see. Task 2 already plays the theme twice and then stops, and then it's done. So that means it should run once, okay? Because the definition of task 2 is playing the theme 2 times. So run task 2, but it should then stop. Now you may have to modify those tasks just a tad to tell them to stop when they're done. That task, not task 1, but you may have to modify task 2 and tell it so that it asks to stop when it's done, which is one line. And remember, we talked about this up in the anyway. That's what that should do. And then after task 2 is done, start task 4 to count down for 3 seconds. And task 4 is combining 2 and 3. So I can see that it's complex. And so what's unspecified in task 3, the 7-segment display counts down until the music starts, right? And so what's unspecified here is how long to count down before it starts. So that would be count down for 3 seconds and then start task 2. And then there's the smile. It's just a different set of bits into the 7-segment display after task C, part C completes. This 2 seconds begins after the completion of 5C. So it's kind of like at the end, there's a smile, and that's it. Does that make sense? Does that clarify it at all?
Yeah, I think I get it. So we should be building task 4 in a way that allows us to start it and stop it where the countdown is variable, because right now I have it like hard coded, and I could hard code it to, like, at first only count down for 3 seconds instead of, because just when we have just task 4, we have it counting down for 4 seconds. So that's how I have it coded initially. But I would have to change some of the code of task 4.
No, because here's, if you read it precisely, okay, then task 2 plays the theme, pauses for 4 seconds, and plays the theme again, right? That's what it says here.
Mhm. Yeah.
Okay, so it starts the theme immediately. And so what's asked for here is to count down for 3 seconds and then start task 2. I'm sorry. Oh, I see why this is confusing. I'm sorry. Yeah. So this is after task 2 is over. And so I guess what yeah, okay, I see. I guess what I meant here, and thank you for the clarification, and I'm gonna, I'll announce this, that I'm making this change. What I'm gonna say is just start task 2 again after 3 seconds. Does that resolve it to you?
Does the task 4 countdown have to be the correct timing? Like, for example, since it's in tenths of seconds, it should be counting down from 30 to 0.
Yeah.
Okay.
I mean, you just write a countdown that takes any argument, right?
Yeah. I'm just that. Yeah, that's just basically just my question. Like, would we be able to modify task 4 or just make a different function? So, because that wouldn't really be task 4 in that way, but yeah, that answered my question. Thank you.
Um, I'll tell you what, you're right. It's not task 4. I'm just going to say after task 2, start a countdown for 3 seconds. How does that sound?
Yeah, that's a lot more clear. Thank you very much.
Yeah, I'm sorry about that.
No problem. No problem.
So,
Okay.
Professor,
Yeah.
for Part 5C, when we restart task 2 for the one last time, there would be no countdown for the interval between playing two themes, right?
No, task 2 is unmodified, right?
Yep.
So, oh, I see.
So it would just be 4 seconds and doing nothing, is it?
Yeah, I'll say that's acceptable.
Okay. And Professor, I have a question about implementing task 5. So
Okay.
currently my group have like a round robin for task 5 itself, but we feel like that might not be the correct way or the way you expect us to do it.
Well, here's the thing. Task 5 is only demoed on the DDS scheduler.
Mm-hmm.
If you look at this is the specific demos you have to do. Does that make sense? So with any other scheduler, you do not run task 5.
Yeah. What I meant is, so for DDS, our implementation of task 5 itself looks like a round robin. So it's like within task 5, we have an internal timer, and then it will start those tasks like
No,
task
use
2
the
and
time
task.
delay use the sleep function
Okay.
within task 5.
Okay.
The point is to use the new features of the DDS scheduler.
Okay, I see.
And so, yeah, this is just a general point, and you'll see this, like, especially you'll definitely see this with FreeRTOS too. Is that when you have a different scheduler, you have a different way of thinking about writing a task. And you want to use the features that the scheduler gives you to make your tasks work. Make sense?
Yep, I think.
You don't want to
And
write a scheduler within a scheduler.
yeah, that's what we've been doing, and we think that it shouldn't be the case, but we couldn't figure out like what is the correct way to do it. And one last question about the task self-quit function.
Yeah.
For the function, I read on PSI, you say that it should only quit the task itself. So are we allowed to pass any parameters into the function, or it should be just be a void?
If you want another task, if you want a function to kill some other task and make it stop, you can write it, but it's
Okay.
not the same.
Then how would it be able to kill itself if we don't pass in any parameters to this function?
You can figure that out. The DDS knows what task is running. So when that is called, it will change its status to dead. The scheduler can change it to dead, and then it should return. Okay, it will return after that call to kill self, but then there should be a return right after that in the task.
Okay, I see.
So then after that return, the scheduler says, okay, what task do I do next? And that's some other task. But when it eventually gets back to the original task, it will be in the dead status, and so it will not be restarted.
Okay.
Does that make sense?
Yep. Thank you.
Great. Good questions. Everybody's questions are good. And I apologize for the confusing wording. Okay, other questions? All right. See you guys on Wednesday. Good luck with the lab.
Oh, thank you, Professor.
Bye, Sunny.
Bye. Actually, okay, I do actually have a question now that I
Aha,
think of it.
okay. First, the way it normally works is you ask the question and I answer it, and then you thank me. But this is fine too.
Okay, I just wanted to quickly clarify, just make sure I have my right understanding for the scheduler types. So with the round robin, the way that the tasks are built is like each time we run a task, it's like a little tidbit of
Yes.
whatever action we need to do. And then with the synchronized round robin, now that we have the interrupts, are the tasks now like the whole function, or are they still
No,
bite-sized?
it doesn't change anything. It's still, I like that term tidbits. We should call it the tidbit scheduler. Okay. It's great. It's still going to do tidbits, but now at the end of the list, it's going to wait until exactly 1 millisecond and then go to the top again. And
Okay.
that way, all the tasks can count on this is a 1 millisecond loop.
Okay.
So it synchronizes it, but it doesn't change anything else.
Oh, okay. I think we were already doing that. All right, cool. Thank you
Great,
for
even better.
clarifying.
Yeah, you're welcome.
Hey, Professor, there was another question in the chat. I was curious if what the answer was.
Okay.
About the format for the exam, or
oh yeah. To be honest, I've been working on Lab 4, and I really want to get you guys launched on that, and then I'm going to just nail down all the questions about the exam.
Okay.
And we'll give you study guidance and stuff like that. But it looks like it's going to be an exam week in the scheduled regular slot.
Okay, I can relay the information to Seth as well.
Oh, thanks. Okay.
Yeah.
Excellent. Okay.
Thank you.
See you guys.